This is Dr. Carroll, and today's video is an introduction to hashing. Hashing is one of my favorite subjects, as we'll see in later videos, because its efficiency in being able to retrieve an item is order 1. And that's just amazing. Okay, so, but I'm getting ahead of myself. So imagine you're designing a system for a 911 call center. So it needs very fast lookups, and it's infrequent insertions into this database. And the database is huge. What you need is something that can quickly get to where it can look up the system, look up the information, and retrieve it. Okay. And so, but before we get started, we need to lay a foundation of some terminology. Okay. So first off, what is a hash table? Well, hash table is an array. Typically, you can think of it as an array. At least I'll just refer to it as an array. And it's going to contain the items, and we'll assign them by a hash function. Well, now you're asking, well, what's a hash function? And, well, a hash function, which we typically represent with an h of x. So you could expect to see that in lieu of hash function. What it does is it maps the search key of an item to a location in the hash table. Now there's a couple different, when we talk about hash functions, we want to talk about, well, a perfect hash function maps each search key to its own location, okay? And where that's usually not possible, it's only possible if we knew ahead of time all of the search keys. What is more common, what we're more striving for, is a uniform hash function and that's equally likely to map a key to any of the indices in the table. So if K is an index in the table, then the probability that K will map to a position is 1 divided by the table size, and that's the definition then of a uniform hash function. Okay, so we've talked about mapping into the hash table, so now let's talk about collisions. A collision, it occurs when the hash function maps 2 or more items to the same location. Okay, and we'll talk about that. We'll talk about, well, what do we do when we have that? Well, we have collision resolution schemes. And what it does, the resolution scheme is saying, oh, I understand that you were supposed to map here first, but let me mitigate the situation and work things out. It assigns a new location to it, to the keys that are involved in the collision. Okay. Open addressing is a collision resolution method where when one key collides with another, the collision is resolved by finding an address that's open, meaning it's free, that there isn't something already stored there. And that's a common collision resolution scheme. Now that we've established collisions, we can talk about clustering. So clustering is what happens when your hash function is assigning too many to the same index, or if you're using linear probing, which we'll talk about in a follow-along video, that it's a range of indices. Somewhere in that same range, we're going to get primary clustering. Where secondary clustering is when it assigns too many to the same indices. Okay, and we also have load factor, which is often represented with alpha, as indicated here, and that's the current number of hash items divided by the size of the table, how many entries. And it's a measure of how full the hash table is in an open addressing scheme. Okay, so let's take a look at an image to help paint this picture. So if we had here a collection of all the data items in this pool, and they're unorganized, what we do is we take a hash function to say, okay, we want to insert this item, or we want to search for this item, and we have a hash function, and that's going to map it to one of the indices in the hash table, and that will help us to find this item. Now that's the 1000 foot view. We're going to get into more detail with that with following videos, but that'll get us started. So we have a data item X here, and we're going to use a hashing function to map it to an index in the hash table. If we had a different data item, the hash function could map it up to here, and that's where we would find that item. So then a collision would be if we had a Z data item here, the hash function mapped here, well, we have a collision. We were going to try and insert it here, and what do we do? And that'll be the subject of a follow along video. Okay. So now that we've talked about hash functions, we need to talk about what makes a good hash function. Now, as I gave as a teaser at the beginning of the video, one of the coolest things about hashing is that it operates in order one time. So to be able to do that, though, we have to be able to compute the hash function. It needs to be very fast. Consequently, it needs to be easy to compute so that it can be fast. And a good hash function is going to place items evenly throughout the hash table, okay? Because otherwise we're going to get clustering, and we'll have to do collision resolution, and it's just going to take longer. And it should involve the entire search key, okay? A lot of research has gone into hashing, and if you're not using the entire search key, you can have some clustering issues that crop up. Additionally, it should use a prime base if we're going to use a modular arithmetic in the hash function. Okay, so these are the 4 requirements for a good hash function, and you could expect this on the exam. So let's talk about some example hash functions. So we could select digits from a number if the search key is a number. For example, if you had your ID card, we could choose the first 3 digits of the ID. Well, if you pull out your ID and look, many of us have 001 as the beginning of the first 3 digits. That would be a poor example. And using digits can often not distribute items evenly. Much better would be the last 3 digits, assuming that they're assigned uniformly. It depends on how they're being assigned, though, or we could see some interesting behavior. For example, if a university decided to give all of the males an odd ID number and all the females an even ID number, that could have big consequences if you were looking at a class or something and trying to hash on the last few digits. It wouldn't be a good hash function, that it wouldn't distribute them evenly. So selecting digits is often easy, but problematic. There's a term called folding. And what folding means is we're going to sum up the digits. Okay, well then that takes into account the entire search key, but again, it has some problems. A very common, fast, and easy to compute method is modulo arithmetic, where we just take the value and apply the modulo operator to it based on the size of the table. Now the size of the table should be prime so that we don't have some artifacts that are going to lead to clustering. Okay. Now, what if your search key isn't a number, or more of it's not an integer? What do? Well, for example, if it was a character string, what we do is we're going to need to convert it to an integer so that we can figure out the index. And there's a lot of different ways to do that. You could convert the string to an integer, for example, and use modulo arithmetic. And let's talk about a couple different ways to do that. You could use the ASCII values. For example, capital A is 65 and lowercase z is 122, and use those values in lieu of the actual letters, and be able to compute it that way. Similarly, you could just say, well, A is 1 and Z is 26. You need to be able to account for, are we going to use any symbols or things like that? What we could do is we could take the binary representations of the ASCII values and concatenate them together, and that's going to give us a really big number. We just need to be careful that we don't get into overflow with producing really large numbers. A very popular method for a hash function is called random hashing. And the first goal is to transfer the item, the search key, into a large random number. Now, if it's not a number, we need to make it one. For example, if it's a string. And so this comes from Donald Knuth. He's very famous in the world of computer science. In his book, The Art of Programming Semi-Numerical Algorithms, Volume 2. And he came up with this, and this has been repeated many times, and it's a common way of hashing. Now, but we need to be careful when we're selecting the constants here for multiplier, addend, and modulus. So what we do is we start with our item. What we're trying to do is just make it a really large number, and but a tameable number, and that's the modulus operator here. So on a 32-bit system, commonly applied numbers for the multiplier are 25,173. The addend is 13,849, and then the modulus here is 2 to the 16th. Okay. Now, once we have our large random integer, then we'll take it and we'll hash it against the table size, depending on how big the table is, and that'll give us our index into our hash table. Okay. Now, that's it for the introduction. There'll be a follow-on video to discuss collisions, collision resolution, and of course, my favorite, the efficiency of hashing. Enjoy.